On July 9th, 1993, a Friday, at 8:42 a.m., Timmy Thompson woke up. Usually Timmy likes to spend a few minutes in bed, enjoying the cozy feeling of being half awake. But today was going to be a busy day, and lots had to be done before his friends would come over and play games with him that night. He had a game to beat, snacks to purchase, and at least a couple of games to rent. No time to lay about. Tommy had already left for his video store part-time job, so Timmy went to say hi to his mom, who was doing some prep work for future meals in the kitchen.
Good morning, sweetie. Big day today, isn't it?
Yeah, I'm so excited. What time will everybody be here?
Well, according to their moms, they should slowly be coming in starting at 4:30. I'll order pizza at 6, and it's going to be lights out at 10:30 p.m. I know that's a little later than usual, but that's just because it's the weekend and it's a special occasion. Any further questions on the evening plan?
No, ma'am.
Timmy goofily saluted his mother.
Can't wait for the fun to start.
And indeed, wait you will. I know you and your friends will spend the whole evening looking at screens, so I want you to stay away from the digital world, at least for the whole morning.
That was a low blow for Timmy, who had a bone to pick with Super Castlevania from the previous evening and was hoping to get it out of the way before the party started.
But Mom, why?
For the reasons I just mentioned, you little dummy. Don't you have games to go rent and snacks to go purchase anyways? That should keep you plenty busy until lunchtime. Or you could go read your book some more.
So there's no room for compromise, is there?
None whatsoever,
Replied his mom with a large grin.
Here's your bowl of Cocoa Puffs, analog son of mine.
While eating his breakfast, Timmy briefly considered being sneaky and playing something on the Game Boy. But risking the parental ire was not worth it on a day where he would host a bunch of friends. So he sadly decided to put away the bowl, grab his programming book, and settled on the comfy couch downstairs for a morning of intense reading.
Alright, where did we leave it off? I forget this okay. We're definitely in chapter 3. Oh yeah, we're talking about the PCX file loader. Let's maybe go to page 85 and just take it from there. Storing bitmaps. It's good to know how to create a bitmap in VideoRAM, but if that bitmap doesn't contain a picture of something, it doesn't help a lot. Painting the entire VGA palette on the display as a series of multicolored vertical lines is an interesting exercise, but it doesn't do us much good in creating computer games. So how do you go about creating the bitmap? You need a program that allows you to paint images on the screen of the computer and store them on the disk as bitmaps. Okay, they used Deluxe Paint to enhance. What the screen looks like. Ooh, looks gross. Yeah, okay, they talk about run length encoding. You want to turn it on and off, and so you store some bytes as straightforward bitmap and use RLE compression on other bytes. We could invent our own scheme to do this, but there's no reason to do so. There are a number of existing methods. Deluxe Paint 2 Edition uses two different methods for encoding files on the disk. One of these, the IFF format, recognizable by the extension .lbm on the files, derives from the Amiga computer on which DP2E was originally written. Second method, called PCX encoding, recognizable by the extension .pcx on the files, runs with a number of other PC programs. It was originally developed by PC Paintbrush from Zsoft. We'll use PCX format to store bitmaps on the disk. We need a set of subroutines to read PCX files from the disk and decompress them into a format we can display on the screen. This is a good opportunity to learn some of the VGA graphic techniques we've discussed in this chapter and create a useful program in the process. So we're developing a loader viewer program that reads PCX files off the disk and displays them on the screen in mode 13H. What's mode 13H again? Call it a resolution. Oh, mode. Maybe that was in the previous chapter? No, it's the mathematics of animation is in the previous chapter. I guess we just know that our mode is called 13H in the BIOS. Okay. Okay, so we're creating a class called PCX. So we can easily make multiple PCX objects, which will read PCX files off the disk and store them in a 64,000 byte buffer designated by the calling program. To be honest, there's no compelling reason to make the PCS routines a class. We're doing it to learn a little bit about C++ syntax. Really, only one thing we need a PCX class to do for us: read PCX files. The PCX class will be so simple it will consist of only 4 functions, 2 of them private to the class and 1 variable also private. Here's the class definition, which we'll place in a header file called pcx.h. Class PCX, private functions. There's an in file that returns an integer. There's a load image function, which takes PCX files input and a PCX struct. And a returns an integer, and a load palette, which doesn't return anything, which takes again the PCX files and the PCX struct. Then public functions will be the load, which returns an integer, and the compress, which returns an integer. All the parts of the definition are private or exclusive to the class PCX and can only be used within the PCX module. Functions variable declared as public, on the other hand, are available to all other modules that are linked with this one. As far as the other modules are concerned, the class header consists of only 2 functions, load and compress. Because these are the only parts of the class accessible to them. Okay. 256 color VGA PCX file consists of a 128 byte header followed by a compressed bitmap and 768 bytes of color descriptors composing the palette used for the bitmap. The 128 byte header consists of several fields describing attributes of PCX file, such as the color depth and width and breadth of the image, and 58 bytes of padding to round out the header to a full 128 bytes. Because it might be expanded later, so we just want to make sure that there's enough space. Although we make little use of the PCX header in our programs, we can define it as a C structure so that we can access the individual fields within the header should that become necessary. Here's a C structure for the PCX header. The header itself is going to be the manufacturer, set to 0, the version, which we'll set to 5, the encoding, set to 1, bits per pixel, which should be 8, top left corner coordinates, width and height of the image, resolution, horizontal and vertical, which I guess you could gather from these 2 pieces of data, but it might be more convenient to just have it stored there. A 48 component vector that contains the palette, stuff that's reserved, color planes, bytes per line, palette type, and filler. The header data does not require the size of the PCX bitmap to be full screen. There are fields with the header, xmin and ymin, that can be used to define an upper left corner coordinate for the image other than 0, 0, and fields that can define a size for the image other than the size of the pixel matrix. This allows us to create PCX images that consist of a single rectangle plucked from a larger image. However, as noted earlier, we're going to ignore these data fields for now and work only with PCX files containing a full screen image. If you try to use PCX routines developed in this chapter to load an image that doesn't start in the upper left corner of the display and fill the whole screen, you'll decidedly get odd results. Alright, so we define the header structure, so it's incorporated into a larger structure that can hold a complete PCX file header and all. So you define the class PCX. The struct seems to be a different thing, because we're defining that right now. Struct tells you how the various PCX files are built out of stuff. There's the header. There's a pointer to a buffer holding the bitmap, pointer to a buffer holding a compressed version of the bitmap, array holding the palette, and select the compressed bitmap. PCX header is a type of object that we've defined above, so we just say that header is a PCX header struct, okay. Take a look at the role of the C image and the C length variable later in the chapter. In order to read the compressed bitmap file from the PCX file into the image array, we need to know exactly how the bitmap is encoded in the file. Fortunately, the PCX RLE scheme is quite simple. You just see the bitmap data as a stream of bytes, portions of which are completely uncompressed and portions which are compressed using a form of run length encoding. Right. This I remember. Okay, yeah. So if your byte is above 192, you copy it without change. Otherwise, wait, no. A byte value from 192 to 255 signals the start of an RLE pair. If you're not in that range, you should be copied into the bitmap without change. So the idea is that a run of 1, which I guess probably means 2 if we're starting our pointer at 0, would be 192. And then all the way to 255, which would probably give you 56 plus 8, so probably 64 as a possible run length. Okay. A single byte run is 193, so 192 is 0. Okay. And then, if you are above 63 bytes, then you just have to do multiple ones. Okay. Read a byte from the bitmap if the value of the byte is between 0 and 191. Transfer it unchanged if the byte is in 192 to 255. Subtract 192 from the value of the byte. This is the run length. Read another byte and repeat the number of times in the bitmap buffer. Okay. And that's how we decode a compressed one. Wait, I accidentally went back. All right. Okay, so we need a function that will load the PCX information from the disk. So the idea is that there's a PCX file, and it puts the content of it in a buffer. Undecoded, I guess? So we're loading a var character that points to the file name and a PCX struct that points to the PCX, right, which is this. So we can use image, compressed image, and all that. So if file open, you look at file name, 0 binary. I guess the content of it must be binary. There's null, return -1. So if there's no file, return -1. I'm not really explaining what we're doing here, so let's try to understand it. This, I think, is just saying if you try to open file name and you get null, that means there's a mistake, so you should return -1, otherwise you keep going. You move the pointer to the start of the header by doing lseek in file OL or 0L seek set. You read the length of the header of the PCX file that you have. It says read in file and then this. The header member structure is accessed like PCX arrow header. Okay. And then you... I don't know what size it does. Does it just return it? Oh no, this is all one line. It says the red length is you read the header location of your file, which you know is a PCX struct. And you measure the size of the component that's called PCX header and save that into here. If you can load an image, you return -1. Otherwise, you load the palette, and then you close the file and return 0. So have we defined all these functions? I don't know that we've defined all these functions. I don't remember us defining any of these functions. That's okay, we'll figure it out. Okay. Use the function, we must first declare an instance of the class PCX. The earlier definition of this class only created a template for the class. Declaring an instance actually creates an object of the class, which can be used to load PCX files. We declare an instance of the class in much the same way we would declare an ordinary C variable, PCX loader. Now we must call the function load and pass it a file name and a variable of type PCX struct, like PCXloader.load, in quotes, PCX file.pcx, comma, and PCX buffer. The dot separates the name of a member function of a class from an object of that class. Thus, PCXloader.load tells the compiler, as well as the readers of our program, they were calling the member function load of the PCX class to which PCXloader belongs. We must pass the address of the PCX struct using the address operator and PCX struct to the function and not the variable itself. That's because load actually alters the content of the variable. Thus, it must gain access to the variable itself rather than receiving a copy on the stack. The load function accesses members of the structure by dereferencing a pointer to it using the indirection operator. The syntax for accomplishing the dereferencing may look a little peculiar if you've never seen it before. The header member of the structure, for instance, is accessed like this, PCX arrow header. It tells the compiler that header is a field within the structure to which PCX is currently pointing. The load member function calls two additional functions, load image and, we're defining them now, load image and load palette that are private to the class PCX. These functions load the PCX file's bitmap into the array image and load the PCX file color descriptors into the array palette, respectively. The text of these functions appears in listing 3.6. This is load image. We feed it a PCX file and a PCX struct. We byte mode is a constant 0, run mode is a constant 1. Okay. We compute the length of the buffer, or we set the length of the buffer to be 5 kilobytes. We start in byte mode. We keep track of the amount of characters read from the file. We look at the we put a variable for the out byte, for the byte count, and for the buffer. So we start off making sure that we have enough memory. So we say we look at the image field in PCX. we define that to be a new unsigned care of image size, which I don't know where we've defined. Is it in the header? Yeah, I don't know where we're getting image size from. But if doing this returns a null, then we return -1. Then we initialize the buffer pointer and the red length. We say we define the image pointer to be the beginning of PCX image. And then we're like, okay, we're starting at I equals 0. We go all the way up to image size. If we're in byte mode, it means that we look at the next byte, and if it's bigger than 192, we switch to run mode and look at the following byte to tell us the color that we need for that run length. So we're individual byte mode. If we're not past the if we're past the end of the buffer, we point to the beginning. And if the red length of everything we've done so far is the same as the buff length of the buffer, we return out, because this means there are no more bytes left. The out byte is going to be the following byte of the bitmap. If it's bigger than BF, which, so F is 15, and B is 11 times 16. 11 times 16 is 176. 176 plus 15 is 191. So this is 191 in hex. So if the out byte is 192 or bigger, we take the out byte, which again is the byte itself. 3F would be 48 plus 15, which is 63. Okay. What are we ending it with? 3F or let's say it. I really wish they'd give us maybe a little bit more on these functions, but so let's ignore the if and move to the else. So assuming we're not looking at a run length flag, we just move on to the next byte. Am I looking at it right? No. This is that one. This is this one. So we're back to, okay, out byte is, we're looking at the next byte in the bitmap. I have a hard time following where things start and end. So this is an if block. This is an if block. This is an if block. So I think this closes the mode equal byte mode. Oh, so if you're not in byte mode, I see. Okay. So if you were in run length mode, you copy the byte on the image, and if subtracting 1 from your byte count, you get 0, that means you're done copying the bytes and you switch to byte mode. So now assume that you were originally in byte mode and you get the run length flag. Oh, doing this, so we're adding 63 to our byte, which is pushing it past 256. And in fact, the overflow is how much, the run that we're looking at. Okay. So byte counts, now doing this is giving us how many times the byte should show up. Of course, if we're past the end of the buffer, we go back to the beginning of the buffer and read more files. So this little snippet is copied from here. Otherwise, we put in the buffer. No, we look at the next image, put that as the out byte. Now we know that we have a run length, so we know exactly how many times we have it. We save that into byte mode so we can just move on. And then we start in run mode and we just keep copying it until we're done with it. Okay, that makes sense. That makes sense. This idea of the buffer, I guess 5 kilobytes is ultimately smaller than the size of our image, right? Yeah, and so that's why we're like, okay. There's a maximum discrete buffer. And the number of characters read. We have the out byte, which is the next byte for buffer, byte count, which is a counter for runs. We have a buffer of length bufflen. You're pointing image pointer to the image part of the PCX. Oh, okay. I think it's because I don't really know what this read function is doing, but I think what it's doing is literally copying the PCX, the contents of PCX file into the buffer at bufflen. We call that read length. If there are no more, we move out. Otherwise, we have copied the next part into our buffer and we're back at the beginning. So the read length just keeps going. It does not reset. But we just keep doing. Okay. Well, no, because Because then otherwise this would reset every time, right? So you have read length has to be smaller or equal than the buffer pointer for it to work. That's gotta be something in the read function that we don't know, and it's fine. We're just gonna move on. All right, whereas load palette shorter takes a p6 file and a p6 struct. We know that the palette is always 768 bytes from end of file because it's the last thing in our PC extract. Well, there's an int at the bottom, but everything after that should be it. So we just go back 760, because if we're at the last byte, you go back 768, here at byte negative 769. Okay, makes sense. You read all the bytes, put them into an array. And then you're saying for every I from 0 to 255, for every j from 0 to 2, you're thinking 3 times I plus j moving into 3 times I plus j. Confused. Oh, this is a shift that we're doing. Okay. The load image function performs the actual decompressing of the bitmap. It operates in 2 modes defined by the integer constants byte mode and run mode. When the variable mode is set to byte mode, a new byte is read from the disk file. If this byte is in the range 0 to 191, it is written directly on the PCX image buffer. It is the image file to the PCX struct variable pointed to by a pointer parameter PCX. If it is in PCX mode, the previous file byte, which is stored in the variable out byte, is placed in the buffer, but no new byte is read. When a transition occurs from byte mode to run mode, that is, if a byte read in byte mode is in the range 192 to 255, byte count is set to the value of the byte read from the file minus 192, which is the same as plus 63. That's what they're doing here. This value is then decremented in each subsequent execution of the loop until the run is completed and byte count is restored. The data is read from the disk using the library function read. Oh, here it is. Or read, I guess, technically. This function reads a large amount of data from the disk into a RAM buffer. This buffer must then be monitored by the code processing the data. In this case, the buffer is imaginatively named buffer. It's 5k in length. The variable buffer pointer monitors the current position of the next character in the buffer to be processed. When the value of buffer pointer reaches the end of the buffer, another read is executed. The function knows when it has reached the end of the file because the read function returns 0. Load palette functions perform the much simpler task of reading the 256 color description into an array of type character. It is done with a single read into the palette field of PCX. The numbers in the buffer must be shifted left 2 bits to make them consistent with the format required by the palette setting function in the BIOS. Okay, so this is a left shift by 2. Which means subtracting 2? Anyways. Okay. We can use the PCX class to create a simple program to read a PCX file from the disk and display it on screen. The text of the main program module, pcxv.cpp, appears in listing 3.37. So we're including standard input-output, standard library, some other stuff. ScreenH and pcx.h. PCX buff is what we call the PCX struct buffer. PCX loader is a PCX class. We have a main function that will take argv vector and an argc integer. The question is, are there 2 arguments on the comment line? If that's the case, put outputs wrong number of arguments and exit with error. If not, so assuming there are 2 arguments, we're looking whether P6 loader load of RGV1 and PCX buffer. It's like if you can't open it, abort with error. Okay. Those don't happen. We clear screen, all of it. We set VGA mode. We're saving the old mode first because we're going to need to go back to it eventually. Set the VGA mode to 0x13, right? Hex 13. Set palette to be the PCX buffer.palette 0 to 56. We create a pointer to the top left corner of the screen, which I assume what this is. We loop through all the bytes. And we just put on the screen pcxbuff.imagi. And then wait until the key is pressed, and then just go back to the old graphics mode. Okay, and then when compiled, the program must be executed with the syntax pcxview pcxfile.pcx, where pcxfile.pcx is the complete file name of the pcx file that you wish to view. This command line parameter is passed to the pcxview program via the standard RGV program. If you're not familiar with argv, check your compiler manual or read the weights group object-oriented programming in Turbo C++ or the weights group Turbo C++ Bibles. I might need to borrow those from the library too if they have it. It would be good to have like a reference manual to work on, because seeing these two functions is probably maybe a little bit more complex than I thought it was going to be. The short program creates an instance of class PCX and then calls the load function of that class to load a PCX file into the struct variable PCXBuff. Now it calls that setPalette function to set the VGA caller registers to the value in the array PCXBuff.palette. It moves the entire bitmap in the array PCXBuff.image into video RAM. Finally, it calls the library function kbhit, protap in the header conio.h, in a while loop to hold the image on the display until the user presses a key. Compiling and running the program. The compile program is in the included disk under the name pcxview.exe. To give it a trial run, cd the directory to where the files from the enclosed disks are stored, and type pcxview walkbg.pcx. This will give you an advanced look at a PCX file we'll use in a program we'll develop in Chapter 4. If you don't like having surprises spoiled in advance, you can skip this exercise. Mom, I'm reading my book, and I kind of want to just turn on the computer to try some things from it.
Oh, is this your programming book you're reading? Well, I'm sorry, mister, but it's gonna have to wait at least until after lunchtime.
Really, Ma? I can't keep reading the book if I don't open up a computer. Really, Ma? I can't continue reading this book if I don't try this exercise for myself. You want me to learn, don't you?
Nice try. I'm sorry, but the answer is still no. Keep reading it if you want, but you will not turn on the computer until after lunch is over.
Fine. Making it small again. The function compress is a feature of our PCX class that we need to discuss here, though we won't be using it until much later in the book. function takes the uncompressed bitmap in the image folder of the PCX struct and compresses into a smaller bitmap in the cImage field of the PCX struct. This might seem redundant since the bitmap was already compressed in the PCX file on disk. If we needed a compressed version of the bitmap, why not simply use the compressed bitmap from the PCX file? However, there is rationality in our redundancy. We need a bitmap compression method that's faster than that used by the PCX files. In this regard, the PCX compression scheme is less than optimal, so we're going to develop one that is more nearly optimal, at least for the specific purposes of the flight simulator that we'll develop in the course of this book. In the next chapter, we'll examine the topic of transparent pixels. Don't worry about how a pixel can be transparent for now. When transparent pixels are in use, however, they are represented in a bitmap by values of 0. Certain bitmaps that will be in use in the flight simulator will have lots of transparent pixels in them, so it's important that we reduce the amount of time needed to process these transparent pixels, especially considering that these bitmaps will need to be redrawn every frame of the in-flight animation. This is simply a matter of reducing runs of 0 pixels to a run length pair, where the first byte is the run length and the second byte is a 0, to indicate that this is the value to be repeated. Since we won't be compressing any other runs besides zeros, the second byte is actually unnecessary, but we'll include it to make it easier to expand this compression scheme to a full compression scheme at a later date, should we so desire. The PCX compression scheme uses run length bytes only for runs of identical pixels. Our run length scheme will use run length bytes both for runs of identical pixels, in this case zeros, and for runs of differing bytes, which will include runs of identical non-zero pixels as well as runs of completely non-identical bytes. In the former case, the run length byte will be followed by a single byte of 0. In the latter case, the run length byte will be followed by all the data bytes in the run. For example, the compression function encounters a sequence of bytes 177, 98, 245, and 9. It would convert it to a run length of byte 4, followed by the 4 original bytes. Okay, so it would be 4, 177, 98, 245, 9. What good does this do to us? Surely it doesn't reduce the size of the file. In fact, it may actually expand it. But it also increases the speed with which the bitmap can be expanded to the display. Our PCX decoding function needed to check every byte of data to see if it was a run-length byte. With this new compression scheme, the decoding function can copy a run of differing bytes to video memory at the fastest speed it is capable of, which is considerably faster than the speed of the PCX decoder. Since there are two kinds of runs in this RLE scheme, runs of 0 values and runs of non-zero values, we need a way to distinguish between these two kinds of runs. This means we need two kinds of run-length bytes, one for runs of zeros and one for other runs. To distinguish between the two, we'll limit both types of runs to a length of 127 and add 128 to the value of the run-length bytes for runs of zeros. Thus, the decoding scheme will be able to recognize runs of differing pixels because the run-length byte will fall in the range 0 to 127, or 1 to 127 since zero-length runs won't be allowed, and runs of zeros because the run-length byte will fall in the range 128 to 255. The decoding function will need to subtract 128 from this latter value before it can be used. So figures 310 for an illustration of the scheme. Okay, it makes sense. So you're looking at most 127 bytes at a time. And it's like, okay, if there's a run of non-zero bytes, which can be either the same or different, we're just going to copy them as is. If there's a run of zeros, we're just going to ignore them and move on. And just move the pointer. The compression function. Now let's take a look at the function that converts the data in the PCX.image field into a compressed bitmap in the PCX cImage field. The function, which is in PCX.cpp file on the disk, is called PCXCompress and takes a single parameter, a pointer to the structure of type PCX struct, that contains the bitmap to be compressed. Makes sense, we already have the image. It starts off, as most functions do, by declaring some handy variables for later use. We set a value, a run length, and run pointer, which are all integers, and then we put a character buffer. Data will be read from PCXImage and compressed into PCXCImage. Pointers will be needed to mark the current position in both of those buffers. We had the pointer and the C pointer. A large amount of scratchpad memory will be needed for performing the decompression. The function allocates 64K for that purpose and assigns the address of that block to the pointer value C buffer. All right. The new command calls the operating system to allocate the memory block and returns a pointer to the block. If memory isn't available, then the pointer will be null or 0. The function aborts. And it returns an error value of the calling function. Now that the preliminaries are out of the way, we have to begin compressing data, looping through the bytes in PCX image until we have read all 64,000 of them. Though we will represent the length of the buffer by the constant image size, so that it can be changed more easily should this become necessary. So while the pointer is smaller than image size, compressing the data is a matter of reading the bytes out of PCX image and writing the appropriate runs of values into PCXC image. Since the variable pointer points to the next value in PCX image to be read, we can check to see if this value is a 0. If it is, then we've encountered a run of 0. Okay. This is the start of a run. We set the run length to 0. We read as many consecutive zeros as we can find, up to 127 out of PCX image, counting the number of zeros in the run with the variable run length. So while the pointer is pointing to 0, we add 1 to it, we add 1 to the run length. If the run length reaches 127, we break. And if the pointer is bigger or equal than the image size, we break. Because we're either run out of image or we're run out of space for our run length. The length of the run having been calculated, we must read the run length pair into PCXC image. So we're going to say that we do cut C buffer C pointer, and we turn into an unsigned character of run length plus 128 to determine what the length is. Point to the next bit, write 0, point to the next bit. Makes sense. If the next byte in PCX image is not 0, this is a run of differing pixels. As before, we initialize the run length to 0. And we're counting off the pixels will be done by looping the value until the next byte is not a 0. But in this case, the actual bytes in the run must be copied directly to PCXC image. We must first read the run length value to PCXC image, which we're not yet ready to do because we don't know how long the run will be. So we'll mark the spot where the run length byte will be inserted later, saving the position in run pointer. Loop through the run, copying things, and then go back to run pointer and set it to be the run length. I see, okay. So while PCX image pointer is not 0, you put it in the buffer. You increase both pointers and the run length. If the run length is bigger than 127 or the end of the image, you break. And then you go back to C buffer run pointer and insert the run length. This process is repeated until the end of PCX image is reached. Before terminating the function, however, we must allocate memory for the actual PCXC image buffer. Up until now, the scratchpad buffer C buffer has been standing in for it. Since C pointer is pointing at the end of the compressed data, we can use it to determine how long this buffer needs to be. Okay, so we create a new image, which is length C pointer. If there's not enough memory for the buffer, return an error. Allocating memory isn't enough. Of course, we must copy the data, right? So we created C image, and then we just do a mem copy of PCXC image of C buffer, starting at C pointer. Of length C pointer, I think. No, sorry, of length C pointer. Delete the buffer, set the C length to the value of C pointer, return. Okay. This was much better. I wish I did this for the previous functions too. I guess he hasn't written them, but. Decompressing the data. The compression function is useless without a corresponding decompression function. We don't need to decompress this data for any of the programs in the next several chapters, however, so we'll postpone the decompression function until we discuss the flight simulator later in the book. For the record, however, the decompression function is quite simple. It checks the run length byte and either writes the runs of zeros or copies the run of the differing bytes, depending on which is appropriate. On the compression function, this is almost trivial to implement. The main challenge will be making it run as quickly as possible, as you'll see. Building the program. To recompile the pcxview.exe program, enter the Borland C++ CDE, change the directory that contains the code from the disk included with this book, enter the chapter 3 directory, and open the pcxview.project using the IDE project menu. Choose run from the run menu, compile, and execute the Chapter 4, Making It Move. If you know how motion pictures work, then you're ready to understand the basic principles of computer animation. Pick up a strip of motion picture film and look at it carefully. You do have a strip of motion picture film lying around, right? If not, look at the strip of motion picture in figure 4.1. The film consists of a series of frames, each containing a still picture. When these still pictures are projected in rapid sequence on a wide screen, they give the impression of motion. Where did this motion come from? There's obviously no motion in the still frames that make up the strip of film. Yet somehow we perceive motion when we see the same frames projected on a screen. The motion, in fact, is in our minds. Each of the still pictures on the strip of motion picture film is slightly different from the one before it, and our minds interpret these differences as a continuous motion. But what we are seeing is a sequence of still pictures. For instance, the film in figure 4.1 shows a figure walking from left to right across the frame. In the first frame, the figure is near the left edge of the frame. In the second, it's near the center. In the fourth, it is in the center. Walking left to right. Aren't they walking right to left? Is it maybe flipped when you project it? Is that why it is? If we were to view this film on a projection screen, it would appear that the figure was gliding smoothly from one side of the screen to the other, when in fact the figure is actually moving across the frame in a series of discrete jumps. But our brains, which expect to see continuous movement, obligingly fill in the blanks in the sequence. We see motion where no actual motion exists. Early movie animators like Mike Fleischer and Walt Disney understood that the image in a motion picture frame didn't even have to be a real picture. It could be a drawing that bore only a passing resemblance to things that one might see in the real or imagined world. If these images moved in a realistic manner, the audience would accept them as every bit as real as human actors. The trick to making these drawn images seem to move was to draw the image in a slightly different position in each frame, so that an illusion of motion is produced in the minds of the viewers. If these animators can make fantastic images come to life on the screen, we should be able to make equally fantastic images come to life on a computer display. Motion pictures, computer style. In Chapter 3, we learn how to draw pictures made of bitmaps on the computer's video display. In this chapter, we'll make those pictures move. There's no motion picture projector or movie film inside a computer, but computer animation is nonetheless produced on a frame-by-frame basis, just like motion picture animation. To show motion on a computer screen, we draw a sequence of discrete images on the display, one after another, changing each image in such a way as to produce the illusion that something is moving on the screen. Much of the animation that you see on the video display of a computer, and almost all the animation that you see on the dedicated video game consoles, such as those manufactured by Nintendo and Sega, is performed with graphic objects known as sprites. The 3D animation routines that we develop in this book won't use sprites, but we'll discuss them briefly in order to illustrate the animation principles that we will be using. What is a sprite? In the generic sense, a sprite is a tiny figure in the computer's video display that can be moved against the background bitmap without disturbing that bitmap. Mario the Carpenter, here of a popular series of games available on the Nintendo video game consoles, is a sprite. Some computers have special hardware that will move spread images about on the screen with minimal effort on the part of the CPU, and surprisingly little effort on the part of the programmer. Alas, the IBM PC has no such hardware, so we'll have to write a special set of routines for sprite animation. Sprites are ideally suited for implementation using object-oriented techniques, since sprites are objects on the computer screen. In this chapter, we'll develop a sprite class that we can use to animate sprite images on the computer's video display. Unlike the simplistic PCX class in the last chapter, the sprite class will be a full-fledged piece of object-oriented programming, OOP, illustrating many of the concepts of OOP code. All details of the sprite implementation will be hidden, encapsulated in the sprite class, so that the calling routine need merely invoke the object of the sprite class and the sprite will appear magically on the screen. Bitmaps in motion. At the simplest level, a sprite is nothing more than a rectangular bitmap, like the ones we've discussed earlier. The sprite bitmap is generally quite small, much smaller than the screen. Some impressive animation has been produced on computers such as the Commodore Amiga using sprites that take up a substantial portion of the video display. The larger the sprite, the longer it takes to animate, especially on a computer that offers no special hardware support for sprite drawing. Programs with big sprites tend to run much more slowly than programs with small sprites. In this chapter, we'll use relatively small sprites. Figure 4.2 shows an enlarged image of a sprite as a walker man. The original and expanded sprite seen in the upper left corner. Although shown here in grayscale, the original version of the sprite is a multicolor image suitable for display on the VGA 256 color mode 13H. In fact, the sprite is part of an entire sequence of sprites stored on the enclosed disk in a PCX file called Walkman PCX. You use the PCX viewer we developed in Chapter 3 to view this file. Of course, the image that you see in Figure 4.2 is represented in the computer's memory as a bitmap. As with other Mode 13H bitmaps, each pixel in the bitmap consists of a single byte value representing the color register that stores the color descriptor for that pixel. This particular sprite is arranged in a rectangle that is 24 pixels wide by 24 pixels tall. Thus, the bitmap for the sprite consists of 24 by 24 or 578 bytes. We can store such a bitmap in an array of type character. To animate the image, however, we must have a way to put the sprite bitmap on the screen and make it move. Putting the bitmap on the screen is easy. We just have to copy the bitmap to the appropriate location in video memory as shown in Figure 4.3. Making it move is trickier. A moment ago, we said that animation is a matter of putting a sequence of images on the screen and changing each image in such a way that they seem to move. We don't have to change the whole image for each frame of the animation, just the part or parts that move. With sprite animation, the part that moves is usually just a sprite, so only the sprite itself is to change from frame to frame. The simplest way to animate a sprite is to draw the sprite in one position, leave it there for a fraction of a second, and erase it and draw it in a new position. By doing this repeatedly, the sprite will seem to move across the display. Erasing the sprite is the tricky part. Usually we will want to animate sprites against a detailed background, and we must be careful not to erase the background along with the sprite. Unfortunately, the background is obliterated by the actual art of drawing the sprite in video memory. The trick is to save the background before we draw the sprite, and then erase the sprite by drawing the saved background over the top of it, as in Figure 4.4. Copy background to buffer, sprite over background, erased sprite. Okay. A structure for sprites. With that information, we can create a data structure that will hold all the information that we need to draw and animate a sprite. The structure will have 6 members. It will contain a pointer to the array that holds the sprite bitmap, and hold a second pointer to a similar array that can be used to store the background image, which is obliterated when the sprite is drawn over it. Since we'll want to animate sprites of varying sizes, the structure will have 2 integer fields to hold the width and height of the sprite in pixels. Finally, we'll need 2 more integer fields to hold the XY coordinates of the upper left corner of the sprite so we know where to draw the sprite on the screen. Okay. Ordinarily, all of this information can be placed in a structure like this. With C++, however, these fields can be encapsulated as private variables within a class instead of public variables within a structure. As many instances of that class can be then declared as their sprites. Let's see how this is done. Building a sprite class. In C++, a class consists not just of a data storage, but a function, called member functions, for operating on that data. For a sprite class, we'll need a function for putting the image of a sprite on the video display at a specified position, and a function for erasing the sprite when it's no longer needed. The first of these functions will also perform the task of saving the background behind the sprite. Thus, to erase the image, the second function will need to copy this background over the sprite, getting rid of the sprite and restoring the background at the same time. Before either of these routines can be called, however, we'll need a constructor, a function that is called automatically whenever an object of a class is declared, that will reserve memory for the sprite data and initialize certain data values. And we'll need a function that can copy sprite bitmaps from specified positions of a PCX file and store those bitmaps in arrays. Technically, such a function is called a sprite grabber. Each object in the sprite class will also own a pair of private arrays called image and save buffer, which it will use to store the sprite data and the sprite backgrounds respectively. Because we'll define image as an array of pointers, which will in turn point to the actual buffers holding the sprite images, it can be used to hold multiple images of the sprite object, which can then enhance the sense of motion. We'll talk more about that later in the chapter. Here's a declaration for the sprite class. Sprite private contains the var character, which is the image, the width and height, x and y coordinates, and a var character, which is the save buffer. And then public will have a constructor called sprite of integer num sprites, integer width, integer height. The sprite grabber function, which grabs as for inputs a unsigned character var buffer, a sprite number, and 2 coordinates. A function that puts the sprite on the display, depending on the sprite num, 2 integers and the screen pointer, and then one to erase the sprite image, which just has the screen pointer. The constructor sprite is the simplest of these member functions. The constructor for a class is called automatically whenever an object of the class is declared. In this case, however, it will also be necessary to pass several parameters to the constructor, telling it how many sprite images need to be stored and what the width and height of those images will be. The constructor then uses these numbers to determine how much memory to set aside for the image and save buffer arrays. Here's the text of the constructor. Sprite has 3 integer num sprites wh. We create a new character var, which is an array based on with as many entries as num sprites, and width and height, and save buffer, which is a new character array of width times height. That was simple enough, but now things start getting complicated. It's time to put together a function to draw a sprite on the video display. A simple sprite drawing routine. If all we needed to do in drawing a sprite was to move a rectangular bitmap into a specified location in video memory, we could do the job with this relatively simple piece of C code. We compute the offset to figure out the sprite coordinates memory offset. And then we're like, okay, for each row up to the height, for each column up to the width, you do screen offset plus row times 320 plus column equals to the image number of the sprite, and then you take the row times width plus column of that sprite. And so using this, right, you go like, okay, I want the screen location at the offset, which gives me the top left corner, to be equal to, okay, it's the row times 320, which tells you which row you're in, plus the column, and I'm going to write that entry in sprite num. In this fragment of code, image is a 2-dimensional array that contains the sprite images. Sprite num is the number of sprite image that we wish to display. Screen is a pointer to either the video screen or an off-screen buffer in which the video image is being constructed, and the x and y screen coordinates of the upper left corner of the sprite. After the video memory location of the upper left corner of a sprite is calculated on the first line, the data for the sprite bitmap is copied to a video memory with a pair of for loops, which use the height and width variables to determine how many pixels to copy. The final line of this routine copies the current pixel value stored in the sprite num element of the image array to the current screen position. In this way, the sprite bitmap is copied to video memory. There are 2 problems with this simplistic approach. The first is that it doesn't save the background. This can be remedied by adding a line to the code that reads, save buffer row times width plus column equals screen offset plus row times 320 plus column. If we place this line directly in front of the line that copies the sprite pixels to video memory, it will save each background pixel in an array called save buffer a fraction of a second before we obliterate it. Transparent pixels. The second problem with our sprite drawing code is that it doesn't take transparent pixels into account. How can a pixel be transparent? We've said several times now that the sprite is represented by a rectangular bitmap. Yet it would be awfully boring if all sprites were rectangles. To avoid this, we usually define a certain bitmap value, often 0, as transparent. Transparent pixels are simply not copied onto video memory. Whenever a pixel in the sprite is defined as transparent, the background image shows through. This allows us to create a spread image in any shape we want, as long as that shape fits inside a spread rectangle. See figure 5 for an illustration of this concept. It's not enough, therefore, to move the bytes of the spread bitmap into video memory. We must check every byte before we move it to make sure that it isn't 0. If it is, we simply skip over it, leaving the background pixel intact. To accomplish this, we reread the last line of the spread drawing code as 2 lines. The first reads the current pixel from the image array, and the second writes the pixel value to the display only if the value is non-zero. Except that it's saying define pixel to be image spread number s offset plus plus. Remember them defining a screen offset variable. I guess it's not a big deal, but kind of annoying. And then if the pixel of screen at p offset is equal to the pixel, you set the picture offset plus plus. Before we present the final version of the routine, there's another problem that we should solve. Animation is one of the most time-consuming tasks that we can add to the computer to perform, and so our routine should be fairly optimized to avoid slowing down the CPU unnecessarily. As written, the sprite code that we've seen so far is reasonably fast, but nowhere near as fast as it can be. For instance, we recalculate the position of each pixel both in the image buffer and on the screen for each iteration of the loop. We really only need to do this once. At the start of the routine, we can establish one variable that can serve as an offset into the image buffer. We'll call this variable soffset for sprite offset, and a second variable that serves as an offset into video memory, which we'll call poffset for pixel offset. Now we simply increment these variables on every iteration of the loop, giving the video memory offset an extra increment at the end of each line of pixels to point it to the beginning of the next line. This is done by subtracting the width of the sprite from 320, the width of the display, and adding the difference to the video memory offset, like this. We are now freed from having to recalculate the position of the pixel on every pass through the loop. Putting sprites. Listing for 1 contains a complete spread drawing function, which we've called put, and have declared as a member of the function class sprite, which incorporates all of these changes. Put takes a sprite num, which is an integer, 2 integers x and y, and a pointer to screen. It's going to draw a sprite on screen with upper left-hand corner coordinates x, y. 0 pixels are transparent, i.e. they're not drawn. So we start by calling the pixel offset y times 320 plus x, which tells us where our top left corner is. And then we set the screen offset to be 0. The sprite offset to be 0, okay. The offset is the actual screen, soffset is just our picture. And then we start at row 0, as long as row is smaller than height, and column 0, as long as column is smaller than width. We're going to save buffer the current position of our pixel, the screen offset. And we're going to make that equal to the screen pixel that we're at. Right? So we start off, and starting top left corner of the screen gets saved into position 0 of save buffer. Then we look at image sprite num, and we look at the next pixel in the offset. If it is not transparent, we're going to place it in the screen buffer, and then we're going to add 1 to the picture offset. Once we're done with all the columns, we set poffset to be 320 minus the width, so we kind of just go back to the beginning of the row. And then we repeat, right? Now we move on to row 2 and do all that stuff. And then we finish with the current coordinates of the sprite. X sprite equals X, Y sprite equals Y. That's weird. What are we doing with that? Because this is a void function. We've added some code into this function to record the current coordinates of the sprite and the X sprite and Y sprite variables. These will be used by the erase function to calculate the position of the sprite in order to erase it from the display. The put function is called with 4 parameters: the number of the sprite and the sprite array, the XY coordinates in which the sprite is displayed, and the address of the video screen. Once again, this allows us to draw from an off-screen buffer should we desire. We'll have more to say about that in a moment. Our X sprite and Y sprite, oh, they're part of the class itself. Okay, so that's why we can do that. They're just saved as part of our class. And these are just the starting position of the sprite. Okay. Erasing sprites. The erase function is a lot simpler than the put function. It is not concerned with transparent pixels or background pixels. Merely copies the background pixel saved by the put function over the sprite image, effectively removing it from the screen. So we just have the pointer at the screen. We calculate the offset as y sprite times 320 plus x sprite. The offset is 0. I still think the offset is poorly named, but. And then, we're doing row and column this time instead of column and row. But I guess it doesn't really matter. And all we do is that we put the save buffer as offset next value into screen v offset next value. And then at the end, are the rows and columns swapped in this particular one? Because you position the pointer on the next line. You do that once you're done with a row? Well, but it's doing this once it's done with a column, though. Not entirely confused, but not entirely convinced, but let's just move on. Function should be called before a new image of a sprite is drawn on a new position, or the sprite will leave a trail of old images behind it. This effect can be interesting under certain circumstances, but it's not the effect we usually wish to produce. Grabbing sprites. The job of a sprite grabber is to grab a rectangular bitmap out of a larger 64K bitmap and store it in an array. We can create the larger bitmap by using the pcxload function that we created in the last chapter to load a pcx file from the disk. We then call the sprite grabber, will pass the address of the buffer holding the large bitmap, position it in the sprite array in which to store the sprite bitmap, the coordinates of the sprite rectangle within the larger bitmap, and the dimension of the sprite. Listing 4 represents the text of the sprite grabber. So we give it the buffer, we give it the sprite num, x1 and y1. We're going to start by allocating enough memory to save the sprite and store that into image sprite num. Then we're going to check whether we're past the screen width or height, and then abort if we do. And if not, if we just go through every row and every column, we look at the buffer in row y1 plus row times screen width plus x1 times column plus x1 plus column. This is going to give us the location of the thing, and we're going to copy that into image sprite num row times width plus column. That's our sprite class. The members of the class are summarized in table 4.1. We'll store the class declaration in the file sprite.h and the text of the member functions in sprite.cpp. Now let's write some code that uses these functions. The sprite itself is a constructor. Specifies the number of sprite images, the width and height of those images. Grab removes the sprite image from a 64K bitmap and places it into the image buffer. It needs a pointer to the buffer, the position of the sprite images within the image buffer, and the x and y coordinates of the upper left corner of the sprite image within the 64K buffer. We need, then there's the put that puts it on the screen, and then there's the erase, which erases the sprite from the screen. The Walkman cometh. Earlier, we suggested you peek into the file walkman.pcx using the PCX viewer that we developed in the last chapter. If you did, you saw 7 pictures of a tiny walker. To demonstrate our sprite class, we'll use 3 of those pictures, we'll save the rest for the next chapter, to create an animation of a man walking across the screen. We'll grab those 3 pictures, the 5th, 6th, and 7th images from left to right, by using our sprite grabber. Then we'll put those images in mode 13H display using the put function of the sprite class. We can create the illusion that the sprite is moving from the left side of the display to the right by putting the first image near the left side of the display, erasing it a second later, putting the second image a few pixels to the right, and so forth. By switching back and forth between images of the sprite with its leg extended and images of the sprite with its legs together, we can also create the illusion that the sprite is striding as it moves. That's what we call the sprite Walkman. Buffering the screen. There's one flaw in the scheme. Because we erase the old sprite image before we draw the new image, there will be a fraction of a second during which there is no sprite image on the video display. As a result, the sprite will seem to flicker on and off very rapidly. Our sprite drawing and erasing routines are fairly fast, which will minimize this effect, but it won't get rid of the flicker altogether. The only way to eliminate sprite flicker is to draw each frame of the animation in enough screen memory buffer and then move the entire screen, or at least a portion of it on which the sprite is walking, into video memory all at once. By updating the screen in this manner, there will never be a moment when the sprite is missing from the display. One frame of the animation showing the sprite in one position will be smoothly copied over the previous frame of the animation showing the sprite in a different position. This is done so quickly that no flicker is evident. To achieve this, we'll create a function called putBuffer, which will move a section of the off-screen buffer into video memory using the Borland C++ library function memmove, which moves chunks of memory at high speeds from one set of memory address to another set. This is roughly equivalent to executing the ADX86 assembly language instruction move, one of the string instructions that we discussed in the previous chapter. Later, we'll rewrite the putBuffer function in the machine language and put it in the screen.cpp file, but for now we'll write it in C++. The putBuffer function is in listing 4.4. It's a void function. It takes a var character, which sends to the screen buffer, and one integer y1 and a height. And what you do is you look at the video memory, and you save that onto the screen pointer. And then you do memmove screen plus y1 times screen width, screen buffer plus y1 times screen width, height times screen width. Since we won't necessarily want to move the entire contents of the video buffer into video memory, this function allows us to specify only a portion of the screen, so that portion must extend fully from the left side of the display to the right. The function takes 3 parameters: the address of the video buffer, the vertical coordinate of the uppermost line of the screen to move, and the number of lines of pixels to move. In this program, we'll just move the section of the screen in which the Walkman does his walking. Constructing a sprite. Most of the rest of what our Walkman program will do involves calling the member functions of our sprite class. We'll first create an object of the sprite class, what we'll call walkSprite. The sprite class constructor will be automatically called when we declare this object, so we'll need to pass the constructor a parameter telling it that we'll be grabbing 3 images of the sprite. Sprite walkSprite, numSprite, sprite width, sprite height. Early in the program, we'll need to add the integer constant called numSprites and set it equal to 4, like this. Then we'll load the walkman.pcx file into a buffer that we'll call pcx and call the sprite grabber to grab all 3 sprites from the bitmap using a for loop like this. You're going to take, for every integer from 0 to 2, walkSprite.grab the image, I, and then I times sprite width plus 4 times 24 is 0. Sprites are on the upper portion of the PCX file, starting in the upper left corner, with additional sprites following every 24 pixels from left to right. The code will calculate their positions and grab them. Once again, we'll need to declare constants early in the program and equate them to the width and height of the sprites in pixels. What does our grab function do again? Oh, this is saving the spread that we're grabbing into the specific number. We're starting after full sprites, and then we're taking I times sprite width. Okay, I see. Alright, setting up the walking sequence. One of the trickiest parts of this program, but one that fortunately has an elegant solution, is determining the sequence in which to display the images of our Walkman sprite. Once we've grabbed the 3 images of the sprite, the walk sprite object stores them in an array as elements 0, 1, and 2. Element 0 is a picture of the sprite with legs apart, element 1 is a picture of the sprite with legs together, and element 2 is a picture of the sprite with legs apart again, extending the opposite leg from that extended in element 0. We want to display these images in the sequence 0, 1, 2. Then we'll need a 4th frame showing the sprite with legs together again. For that, we'll use element 1 again. To make the sequence easy to access within the animation code, we'll define an integer array called walk sequence like this: 0, 1, 2, 1. You can see these sequences, walking left, walking right, or standing still, in figure 4.6. Now we can, looping through a sequence. Now we can set up an infinite loop using the old C trick of creating a for loop with no parameters, like this, for. This will animate the sprite until the user presses a key. Here's the animation loop. So for, and then you're like, okay, for j going from 0 to 15, for I going from 0 to 4, so 15 frames times 4 different sprites. We're going to put walk sequence I at position j times 20 plus I times 5. What does put do again? The sprite number, x and y are the 2 integer of the location, and then they're calling the screen. So the x coordinate is going to be j times 20 plus I times 5. The y coordinate is going to be 100, and then screen buff. And then we're going to put buffer, screen buff, 100 sprite height into video memory, right? So this is looking at we're at line 100, height 100. We take the sprite height and we put that on the screen. For long, d equals 0 up to delay d++. So you're holding the image for the count. You erase the image. If you see a press, you abort. And the same thing for all of them. We have to check 3 times to see if a key has been pressed because the main part of the code is nested 3 levels deep in for loops. The outer loop repeats indefinitely until the user escapes with a key press. The next innermost loop repeats once every 4 frames as the sprite walks from left to right, and the innermost loop cycles through the 4 animation frames using the walk sequence array to determine which frame to display next. Walk sequence I. The check is made with the KB hit function to see if a key has been pressed. As we saw earlier, keyboard hit returns a non-zero value if a key has been pressed by the user. It will continue returning a non-zero value until the keyboard value is read, which is never done in this program. Thus, the keyboard hit value can be read every time break is used to escape from a level of the loop, yet it will still return non-zero each time. Notice that the loop is deliberately slowed with a 4th delay loop, which iterates for a number of repetitions determined by the constant delay. This constant will be set at the beginning of the program and can be used to fine-tune the speed of the animation for a specific machine. If you find that this animation runs too quickly on your machine, increase the value of the constant delay. If it runs too slowly, decrease the value of your constant delay. Incidentally, before any of the above can be done, a background image must be loaded for a sprite to be animated against. Without a background, we couldn't be sure if the transparent pixels in our sprite image were truly transparent, or if the image was properly being erased and the background properly saved. We'll load this image from the file walkbackground.pcx, which is on the disk that came with this book. Walkman struts of stuff. Listing 4.5 contains the complete text for the main module of the program, Walkman. So it includes a few libraries, FSprite, PCX, and ScreenH. 4 sprites, sprite width and height 24 each, will do a delay of 40,000. Prototypes, you have set video mode, put buffer, define PCX and BG as PCX structs, screen buff a far character, and then the walk sequence to be the animation sequence. The two PCX objects to load the bitmaps, Walkman, walk background. And then the sprite, walk sprite itself, with the little Walkman. Then the main function is gonna start by trying to load stuff. If you can, you clear screen, you save the old mode into the old mode variable. Set video mode to 13H, set VGA palette based on the PCX. You load the walk background PCX, which is a background type PCX file, PCX struct. You create a screen buffer. You are going to move the background image to the screen buffer, the background image to the screen buffer, okay? And then you're going to move the off-screen buffer to the VidRAM. You're going to grab the walk sprites, put them in from the PCX image. Then we're going to loop the animation as described above. Then when we're done animating, we're going to restore the old mode. And then we also have the put buffer, which do we call? Put buffer. Unsigned character far screen buff, int y and height. And what it does is that it points at video memory and then moves the, okay, yeah, we used it here, right? And what it does, screen buffer, y location, y height. Okay. When you run this program, you'll see the Walkman sprite walk across the screen against a texture background. Press any key when you're tired of watching the little fellow strut stuff. Although this may not look as spectacular as a full-fledged video game, it embodies many of the main principles used to produce such games. If you have a mind to write a Super Mario Bros. Style game for the PC, these sprite routines will get you off to a good start. Should you want to start off a bit smaller and simply tamper with the Walkman program, load the walkman.project project file into the Borderlands C++ IDE and use it to recompile this program. Although 3D animation doesn't use sprites, it follows the same principle that we've illustrated in this program. Our 3D animations will be constructed as sequences of frames, in which each frame is constructed in an off-screen video buffer and moved into video memory to avoid flicker. Each frame will depict a slightly different portion of an animation sequence, creating an illusion of motion. Before we get into 3D animation, however, there's one more topic we need to cover, the user interface. In Chapter 5, we'll introduce our Walkman sprite to the 3 forms of input commonly used in PC computers: keyboard, mouse, and joystick. Building the program. To recompile the Walkman exe program created in this chapter, enter the Borderlands C++, change the directory to the chapter 4, open Walkman project, and run.
Timmy looked up from his book to check the time. 10:30 a.m. already. He glanced at the length of the next chapter and decided that if he were actually to beat Castlevania 4 today, he'd have to get a move. He glanced at the length of the next chapter and decided that if he were to actually beat Castlevania 4 today, he'd have to get a move. But he wrote down the names of the two C++ references that the book mentioned, figuring he might check them out at the library. He then went upstairs to grab the Shadowgate clue book, since he had no further need of it. And having said goodbye to his mom, he grabbed his bike and went downtown. On the ride over, he considered in which order to tackle his chores for the day.
The video store should probably be last. I don't want to risk losing any game rentals on my way home. I guess Mr. Anderson's shop is right next door, so I might as well just stop there too. If the press is right, I might get myself another game or two. Oh, and I need to get some treats for the evening. Maybe the candy store? Oh, and then I have to drop off the books from the library.
Thinking about the map of Arkport he had in his mind, Timmy decided to stop by the candy store first. A few minutes later, Timmy was $3 lighter, but had a mix of candy bars and penny candy that would keep him and his friends full of sugar all night long. He popped the bag into his bike's basket and kept going towards the library. As he went by the newsstand, he spotted a new issue of Computer Gaming World hanging from the stand.
I really like the one issue of magazine I've read.
Thought Timmy.
After all, that's what got me started on the whole programming business. I wonder how much the new issue costs.
As he approached the newsstand, a gruff voice cried out.
Keep your grubby hands away from the magazines, and if you flip, you buy.
Old Man Crab never had much of a business sense in Timmy's mind. He didn't know how someone so gruff with clients could have a client-facing business. His mannerism usually intimidated Timmy, but he kept his distance, and in a moment of courage, he stared down Old Man Crab and said,
Good morning. How much for this magazine? It's written on the cover. What are you, blind or dumb? Pick one. Deep breaths, Timmy. He's all bark and no bite.
Thought Timmy to himself, as he glanced at the barcode on the magazine's cover.
It says $3.95 in the corner. That's before sales tax.
Mr. Crab typed a few numbers on his calculator.
Comes out to $4.18 after it. Here you go.
Said Timmy, pulling out a $5 bill.
And here's your change. Pleasure in business. Don't think you can start touching the other magazines just because you bought one. Now scan. Have a good day.
After saying this, Timmy turned around and walked as quickly as he could towards his bike without losing his dignity. As he climbed onto his bike again, he could still feel his hands shaking from the encounter. But he had successfully bought a magazine at the newsstand by himself, which was a big step in getting over his fear of Old Man Crab. A few minutes later, Timmy is in front of the library, his composure regained. One thing is for sure, he was excited to see Mr. Potter's friendly face after all this.
If my eyes don't deceive me, that is young Timmy coming through the door. How can I help you today, Timmy? Hi, Mr. Potter. I came to return this book I borrowed the other day, and I was curious if you had a couple of other books I've been looking for. Why, of course. Just hand the return and I'll take care of it later. Now, what books are you looking for? There are a couple of programming books on C++. One is called... Give me a second.
Timmy pulls out the note from his pants pocket.
The Weights Group Object-Oriented Programming in C++. And the other is the Weights Group Turbo C++ Bible. I see. Let me think for a minute.
Mr. Potter went to his filing system and opened a couple of drawers.
I believe it should be in section 5. Go upstairs and turn right and look at the second stack on your left. You might need to look around a little bit. I'm not as familiar with this specific field to know what you're looking for. But if you need a hand locating a book on the stack, just let me know. Thank you, Mr. Potter.
And, as is usual, Timmy rushed in the direction pointed by the librarian. After a few minutes of perusing the stacks, he found one of the books he was looking for, but not the other.
Alright, here it is. Object-oriented programming in Turbo C++. Let's see. Introduction, big picture, loops, structures, functions, graphics, pointers. Okay, this is cool. This could be a good reference. Let me look at the index. We're looking for ARGV. Oh, AirJC 542, AirGV 542. Okay. 542. The system stores the command line arguments as strings in memory and creates an array of pointers to use those strings. The example in the errors code is ARGV for argument values. Individual strings are accessed to the appropriate pointer. So the first string, the path name is RGV0, the second is RGV1, and so on. ARGC for argument count represents the total number of command line arguments. Okay. Okay, yeah, it seems to have like a pretty good and thorough index. You can see the functions are in this weird script, so you can easily find them in the index too. Alright. So that's one of them. What else is around? Can we find the C++ Bible? No, I don't see it. Ooh, what's this one? C++ programming language. Picture of this book. Index at 633. What is this one? C++ programming language. Doesn't look like different. 633. AirGC, AirGV485. Let's see how it explains these. In the latter form, AirGC shall be the number of parameters passed to the program from an environment in which the program is run. If AirGC is non-zero, these parameters should be supplied to zero-terminated strings in AirGV0 through AirGV, AirGC-1, and AirGV0 should be the name used to invoke the program or blank. Yeah, I don't like this one as much. It's probably a better book if you're into it, but the other ones seem to have a better. This is, to me, this is not the first book you should read on C++. So, what about this one? Programming Windows games with born in C++. Ooh. Another recent one, too. This also looks more like, what if you already know C++ and want to specifically program games? Yeah, I don't see ARGV or RGC explained in this one. Okay. This one is not gonna work. Alright, well, it looks like our choice is made, and we're gonna go ahead and borrow this one. Robert LaFleur.
Having made his choice, Timmy brought the book to Mr. Potter.
Found what you were looking for, I take it? Close enough, I think. I'd like to check this one out. Of course, Timmy. Please hand me your library card so I can record your loan.
Timmy pulled up his wallet, found his card, and handed it to the librarian.
Here you go, Mr. Potter. Your car's getting a lot of use these days. Remember that your Flights of Fantasy book is due in 1 week. We have no outstanding requests at this time. Would you like to renew it? Oh, yeah, that would be great. I'm borrowing this book as a reference for some stuff on that one, so I'm far from being done with it. Well, of course. Let me mark it down on the card.
Mr. Potter scribbled the updated due date on the book's card.
Alright, you have successfully checked out your new book and renewed the old one for 2 more weeks. Can I assist you with anything else? No, Mr. Potter, thank you so much for all your help. It's a pleasure, Timmy. We don't see as many people your age as I'd like, so do me a favor and advertise the services we offer to your friends, especially on these warm summer days. Will do, Mr. Potter. Have a good afternoon.
These words said, Timmy left the library, climbed on his bike, and went towards downtown.
Just the games left to rent, and then I can go home and beat Castlevania.
Timmy thought to himself. He still decided to quickly pop into the used game store just to see what was up.
If it isn't the young Master Thompson, welcome once again to my humble abode. Have you brought visitation upon my land to leave richer than you came in, or to help me cover my lifestyle? Hi, Mr. Anderson. I'm just browsing at this time, but willing to buy something at the right price. Rad, dude. Totally rad. Let me know if you have any questions or wish to purchase anything for legal tender.
Timmy started wandering in the shop. Not that there was much to wonder, given how small it was. But sometimes wandering is a state of mind, and Timmy picked up and put down a bunch of boxes as he made his way through the shop.
Anything good here? I mean, we have Mario and Mega Man already. Yeah, none of these look good. Valis looks impressive on the cover, but probably not worth it. What's up with the PC aisle? Ooh, Dungeons and Dragons. Yeah, yeah. I have the Beholder. That one looks cool. And what's this? Oh, is this an Indiana Jones point-and-click adventure? Oh, I bet it's really good.
At the end of the day, there were a couple of games on the PC shelf that seemed to call his name. Emboldened by a successful interaction with Old Man Krat, Timmy decided to do something he had never done before. Haggle.
Hey, Mr. Anderson. What's up, Timmy? There are a couple of games that interest me, but I'm not sure which one to get. Hey, man, I can give some suggestions if you wish. What games were you looking at? Well, the Indiana Jones game looked cool. I heard good things about Pull of Radiance and Eye of the Beholder. The Last Ninja just looks so cool, and same for Ultima Savage Empire. That's quite the selection you have there. I think Eye of the Beholder, Ultima Savage Empire, and Indiana Jones are fantastic. Like, top-notch games. Pull of Radiance is great, but it's a little bit on the old side. And The Last Ninja can be fun, but it's definitely also a very old-looking game. How much do they cost? Well, Eye of the Beholder and Savage Empire are newer, so they're $17 each. The rest of them are older, so $5 for each of them.
Now was the time to start negotiations.
Oh, that's a lot more than I would want to spend today. Bummer. Well, I guess I'll come back another day. See you, Mr. Anderson.
Timmy started turning around and heard Mr. Anderson say,
Wait! Timmy, wait! I've got him.
Timmy thought to himself,
You and your brother are good clients, so maybe there's some compromise we can get to. How much would you like to spend? No more than $20. Tell you what, I'll make a big deal, ruin myself, but I can give you Eye of the Beholder and Pull of Radiance for that. Two fantastic RPG classics. One might be a little older than that. I guarantee you won't even finish by the end of the summer. How's that sound, huh? $2 discount for two fantastic games. I mean, I like Eye of the Beholder, but you're right, the other RPG seems a little old, and I already have two Ultimate games waiting for me at home. I was kind of more interested in Indiana Jones, I think. I don't think I can give you Indiana Jones and Eye of the Beholder for the same price. Indiana Jones is a little more recent and holds better graphically than Pull of Radiance. It goes like hotcakes, really. I'm losing a potential moneymaker if I undersell it. Tell you what if we do 25 and you take home all three, right? So you get two fantastic RPGs and a great point-and-click adventure.
Timmy got very bold and just looked at Mr. Anderson and said,
22.
Tell you what, 24 and I'll throw in the Carmen San Diego game too. Been in the store since February and it's been eating up primo shelf space. Time for the coup de grace.
23, not $1 more.
You drive a very hard bargain, young Timothy. I'll accept it, but know it is because of you that I will go hungry tonight.
Really?
Timmy suddenly worried that he was actively hurting Mr. Anderson. He liked games, but not at that cost. However, Mr. Anderson simply started roaring with laughter and responded,
No, of course not, man. I was enjoying our little verbal sparring and got a little bit too much into it. But don't expect this kind of thing to work again in the near future. I do have to make a profit eventually, and I just sold you 4 games for $23. Alright, let me grab a bag for your PC games while you grab the money.
Timmy pulled $23 from his wallet.
That was the entirety of his gardening money
And his weekly allowance gone, just like that. But he came out with 4 PC games, which would have cost $9 more at sticker price, so he wasn't too disappointed by the end result. Mr. Anderson grabbed the money and gave Timmy 2 plastic bags worth of big box games, saying,
Pleasure doing business with you, young master. Enjoy. Stay chill. Thank you, Mr. Anderson,
said Timmy, before leaving the shop and walking into the video store next door. Tommy was looking bored at the counter. It was clearly too early for kids and families to come in and rent a video for the weekend. As soon as he saw his brother, Tommy waved.
Hey, big bro. How's your work shift going? All quiet on the Western Front so far, little bro. What have you got over there? Oh, I haggled with Mr. Anderson and got 4 PC games for the price of 2 and a little bit more. Impressive, young Padawan. Did you use any force tricks to convince him? No, just some good old-fashioned haggling. And I bought a magazine from the newsstand today, too. You're getting over your fear of old man crap? Big day for old Timmy. What can I help you with, sir?
Tommy had switched to his professional self all of a sudden.
I'd like to rent some games? Of course. Which games are you interested in?
Asked Tommy, pointing at the selection shown on the wall to his left. He then added in a whisper,
My boss was looking at me, so I gotta cut down on the chit-chat.
Timmy nodded, looked at the games for a few seconds, and said,
Definitely Contra 3, then TMNT 4? Contra 3 I can do, but we're out of copies of TMNT. Sorry, little bro. Then I'll pick you in Squadron instead. Alright, hand me your membership card.
Tommy scanned the 2 games.
It'll be $1.50 per day for each of these. How many days should I put you down for? Just one. I'll bring them back tomorrow. Sounds good. Remember, there's a $2 late fee per day, and your rentals expire tomorrow night at midnight. Will do. Here's the $3 I owe you. And here are your games. Thank you for your business. We're looking forward to seeing you in our establishment again soon.
Tommy waited a few seconds.
And tomorrow morning at home.
And he gave a little wink. That was the end of Timmy's chores for the morning. All that was left to do was to go home and get ready for the evening's fun. And maybe beat Castlevania while he was at it.